48 hours after 3I/ATLAS skimmed past Mars Hubble, Webb and Mars orbiters sent back images and spectra that upend expectations. A surprisingly massive CO2-dominated visitor, older than our Sun, steady in its outgassing. Natural giant or an interstellar relic baked by eons of radiation. The size, chemistry, and steady behavior force hard questions, and a rethink of how other star systems build comets. Let's dive right in. The closest look. What actually happened in plain terms? 48 hours after Atlas flagged a fast, hyperbolic dot on July 1st, telescopes across the globe and in space began to follow a pattern that would not be forgotten. Hubble, Webb, the new SphereX mission, and our Mars orbiters each added a distinct piece to the puzzle. One image set showed a compact, steady coma. Spectra showed unusual chemical dominance, and a Mars orbiter, ExoMars TGO, delivered the closest instrument view we've ever had of a confirmed interstellar visitor, a fuzzy dot seen from some 30 million kilometers away. These aren't speculative reports. They're coordinated observations from multiple professional facilities. What the instruments actually measured, and why those numbers are awkward, start with brightness and extent. Optical images, Hubble among them, captured a compact but luminous coma. Not a bright, structured nucleus we could resolve, but a glow whose extent and intensity set off debate about scale. Infrared spectral campaigns, SphereX and JWST's NIR spec, picked out a coma rich in CO2 and showing only trace water, a composition profile that's significantly different from the typical solar system comet. SphereX reported a CO2 coma stretching hundreds of thousands of kilometers. Webb obtained near-IR spectra, confirming the molecular signature and helping constrain nucleus size. Those are the measurements that force the modelers to squint. Why size estimates create a paradox? Photometry-driven estimates gave a wide range. If most of the observed light came from a tiny, dark nucleus, the nucleus would have to be enormous to match the brightness. If instead the light mainly came from distributed icy dust and fragments in the coma, the nucleus could be small, similar to 2I/Borisov. Put bluntly, either we're looking at an unexpectedly huge interstellar rock, or we're looking at a relatively modest nucleus surrounded by an extreme fog of reflective material. Both options strain our prior expectations. The brightness, combined with measured non-gravitational acceleration, or lack thereof, pushes modelers into uncomfortable territory. The observed outgassing rates should produce measurable recoil, but acceleration is small, implying either very large mass or unusually distributed outgassing. That tension is the beating heart of the mystery. Composition as a forensic clue, CO2, water, and the fingerprint of formation. The chemical mix is the clearest anchor we have. Most comets from our system show significant water vapor relative to CO2 when they reach the inner system. This object's coma is dominated by CO2 with very little water. That ratio, combined with detection of water-ice signatures in the nucleus and the presence of metal traces, maps back to two realistic scenarios. One, the object formed in a region where CO2 froze closer to the parent star than water did a different ice line than ours or two. It was processed by extreme space weathering over billions of years, which can preferentially deplete surface water and leave CO2-rich layers exposed. Both are plausible, and both imply an origin unlike a standard Kuiper belt or Oort cloud body. SphereX and JWST results are the backbone for this inference. Trajectory and kinematics. An old traveler with a complicated past, orbital solutions show a hyperbolic inbound path and galactic motion consistent with an object that's been kicked around by many encounters. Velocity components mapped into galactic coordinates indicate high vertical motion relative to the disk, which statistically points to an older population, the thick disk, rather than a young thin disk origin. That's why several teams estimate ages measured in billions of years. It's consistent with heavy cosmic ray exposure and the altered chemistry we now observe. In short, motion and chemistry tell the same story: ancient, long exposed, and far from familiar. Mars orbiters and the unique value of the close pass. Why does the Mars encounter matter? Because ExoMars TGO and Mars Express gave us the only spacecraft-based perspective in situ during closest approach. At approximately 30 million kilometers, the instruments weren't optimized for distant faint comets. Yet the TGO camera sequence produced the best proximate images we've ever gotten of an interstellar comet while active. That view confirmed a broad, symmetric coma, hundreds to thousands of kilometers across. A coma not obviously dominated by jets or explosive fragmentation during the close pass. Practically, ground and space telescopes gave spectra and total brightness. Mars orbiters gave spatial context at a closer vantage point. Together, they constrain the coma's size distribution and rule out immediate catastrophic fragmentation. Mass, non-gravitational acceleration, and the mechanical problem. Here's the mechanics. Measured outgassing rates imply a specific momentum flux. If the nucleus were small, that momentum should produce measurable, non-gravitational motion. Observations put stringent upper bounds on that acceleration. Therefore, the object must either be substantially more massive than a modest nucleus would allow, or the outgassing geometry is nearly perfectly symmetric, which is dynamically unlikely for cometary activity. Modelers run through the numbers and end up with either very high mass, hence the too big estimate, or a requirement for atypical outgassing patterns. Both outcomes demand we accept that this visitor is unusual compared to previously observed comets. Put another way, the math doesn't let us off the hook. Two leading hypotheses, natural formation versus exotic alternatives. Be direct, the community debates two broad explanations. Natural origin, a conventional comet from another star system, formed near a CO2 ice line or heavily processed by cosmic rays over billions of years. This fits the chemistry and the kinematics. It accepts that interstellar comets can be more varied than our small sample implied. It requires no new physics, only a broader view of formation environments. Exotic scenarios, engineered probe, debris from unusual astrophysical events, or a body with atypical density/porosity. These ideas spike attention because they're dramatic, but they face an immediate burden. Spectra show ordinary cometary volatiles and dust chemistry consistent with natural materials. Claims of non-natural alloys or propulsion signatures would need unequivocal, repeatable evidence. And so far, the high-quality spectrographs, Webb, ground telescopes, SPHEREX, favor natural explanations. Reporting that an object might be artificial makes headlines, but it fails when confronted with broad spectroscopic data sets. Look at the instruments. They weigh against exotic claims. Where the twist comes in, the rarity paradox. This is the twist that gives the story real narrative torque. Based on standard population estimates, we expected many small interstellar fragments before a monster like this. Yet our surveys only found 2 prior interstellar objects. Now we detect one that appears massive or unusually active. Either our sampling is biased, we missed swarms of smaller bodies. The production mechanisms of interstellar debris are different than we thought, or trajectories conspired such that a large CO2 bright object was much easier to detect at survey thresholds. Any answer rewrites a portion of formation/population theory. That's a big deal. It's not just an isolated oddity. It's a data point that could rescale expected detection rates for the Rubin Observatory and other surveys. Avoiding sensational pitfalls, what the data do and do not allow us to say, "Oh, responsible editors rule." Separate what is well measured from plausible inference. We have repeated, independent detections of a coma and consistent spectral signatures across instruments. We do not have a resolved nucleus image. We do not have direct isotopic ratios yet published that pin down birthplace, and we do not have signs of engineered structure in the imagery or dynamics. Assertions beyond that, like "this proves alien life" or "this is a man-made probe," leap past the data. The drama should come from the facts and their implications, not from leaps into sensational territory that would immediately alienate a scientifically literate audience. A tighter list of the concrete unknowns left on the table. Exact nucleus, size, and porosity, limited by resolution at closest approach. True mass estimate, tied to unresolved acceleration measurements. Isotopic ratios of key volatiles, COH, pending precise spectroscopic extraction. Internal heterogeneity. Do layers of different ices exist under a CO2 shell? Rotational state and torque, unresolved because non-gravitational signals are small. Each open item is addressable with the next wave of spectroscopic analysis, refined photometry from archived Mars orbiter and high-rise frames, and coordinated observations from upcoming facilities. Those follow-ups are not speculative. They are the natural next steps any rigorous team would take. Drama, predictions, and a grounded bet you can discuss in the comments. Here's a prediction with trackable consequences. If the object's CO2 dominance is intrinsic, formed near a CO2 ice line, then post-perihelion activity should decline slowly. The volatile reservoir is deep and will outgas over a broad temperature range. If instead the CO2 signature is a radiation-processed surface veneer, we should see a sharper decline as the object sheds that skin and exposes more water ice, or the activity pattern could shift. We can test that by tracking brightness curves and spectra in the weeks and months following perihelion. Those observations will falsify one or the other scenario. I'll put this on the table. Vote in the comments. Intrinsic CO2, formation versus radiation-processed surface. Back your vote with one observational reason why. That's the discussion that builds a fan base, not baseless hype. Why this matters beyond novelty, science, policy, and public appetite. This isn't just an astrophysical curiosity. Interstellar comets are the only direct samples we can get of material from other planetary systems without sending a mission there. Each spectrum is a chemical snapshot of a different formation environment. Understanding the diversity of cometary chemistry changes models of planet formation, volatile delivery, and the prebiotic inventory available to planets across the galaxy. Practically, better predictions for exoplanet atmospheres, for delivery mechanisms of organics, and for where to focus future sample return or interception missions. It also makes the case for flexible science platforms, planetary spacecraft that can be rapidly repurposed to squeeze extra value out of serendipitous events. The best quick read of the competing evidence, so you can argue in comments: discovery and orbital status, Atlas discovery, hyperbolic trajectory, and close approach timing. CO2, dominance and extended coma, Spherex and follow-up infrared work, deep spectral constraints, Webb's NIR, SPEC observations and the preprint analyses that followed. The closest approach perspective, ExoMars TGO imaging delivering proximate views from approximately 30 million kilometers. Broader context and population questions, survey expectations and journalist-grade summaries, Reuters/Live Science, that synthesize what multiple teams are saying. A tight, dramatic recap of the middle act, what we've just walked through. We have coordinated multi-instrument detection, an interstellar body with an unusually CO2-rich coma, ambiguous size estimates, small measured non-gravitational acceleration, and a closest approach imaged by planetary orbiters. Each data point rules out simplistic claims and narrows hypotheses. The remaining options force us to rethink either how these objects form or how we detect them. That's the real drama. The data are rich enough to matter, but messy enough to keep experts arguing. Good drama with substance makes viewers stick, which is how you build a scientifically engaged audience, a natural call to action. Invite the audience in. If you're into this and want to help push the conversation, comment below with the one piece of evidence you think is most decisive, composition, trajectory, or dynamics, and share the video with a friend who likes hard facts and bold questions. Good debate builds the best community, and the data will settle the drama, not hot takes. So what happens next? In the coming months, Hubble, Webb, and even the JUICE mission near Jupiter will take one last look before 3I/ATLAS disappears forever into the dark. Maybe it'll reveal new isotopes that rewrite what we know about how other stars form planets. Or maybe it'll prove that our galaxy hides billions of ancient travelers just like it. Either way, this story isn't over. Every new frame, every spectrum brings us closer to understanding our cosmic origins. So, what do you think? Is Atlas a natural relic or something far stranger? Drop your theory in the comments, share this with a friend who loves space mysteries, and make sure you're subscribed to Galactic Breaking News, where the next discovery might just change everything. Stay curious, stay watching. The universe is speaking. We're just beginning to listen.